Black holes. They're kind of like those cosmic vacuum cleaners we all imagine, right?
Right.
But what if I told you that there's this system out there, Cygnus X-3, with a possible black hole,
Uh,
and it's not sucking things in, it's
sure.
actually being blasted by crazy stellar winds?
Yeah.
It's wild, and the XRISM Observatory is giving us a front row seat to this cosmic drama. It's happening 32,000 light years away.
Yeah. And it's not just any drama.
What is it?
We're talking about a rare Wolf-Rayet star, a type of star that's so massive and volatile.
Right.
It's shedding its outer layers at an incredible rate, like a cosmic pressure cooker letting off steam.
Okay, so we've got this crazy star, it's spewing gas everywhere, and then there's the suspected black hole. What happens when these two forces collide?
Imagine a cosmic hurricane. So the black hole's intense gravity pulls in some of the gas from the Wolf-Rayet star's wind,
Okay.
heats it to millions of degrees.
Wow.
That superheated gas then blasts out X-rays, and that's exactly what XRISM, the X-ray imaging and spectroscopy mission, is designed to capture.
So XRISM is basically giving us a glimpse into this high-energy cosmic dance,
Yeah.
right? What's so special about this new observatory?
Yeah?
Haven't we observed Cygnus X-3 before?
You're right. Cygnus X-3 isn't exactly new. It's so bright in X-rays that practically every X-ray observatory we've ever launched has taken a peek. But XRISM is different. It's got this incredible instrument called Resolve,
Okay.
a high-resolution spectrometer that's giving us the most detailed X-ray spectrum of this system we've ever seen.
All right, so we're getting down to the nitty-gritty here. What kind of secrets is this spectrum revealing?
Think of it like a cosmic fingerprint.
Okay.
But instead of loops and whorls, we're looking at peaks and valleys of X-ray energy.
Right.
These peaks and valleys tell us what elements are present in the gas,
Yeah.
how hot they are, and most importantly, how they're moving.
Wait, we can tell how fast the gas is moving just by looking at light?
Exactly. It's all thanks to the Doppler effect.
Oh.
You know how an ambulance siren sounds higher pitched when it's coming towards you
Right.
and lower pitched when it's moving away?
Right. Yeah.
Light does the same thing. When the gas is moving towards us, the peaks in the spectrum shift to higher energies. And when it's moving away, they shift to lower energies.
Okay, so that's how we know the system is anything but calm. What's XRISM telling us about the speed of this cosmic hurricane?
Hold on tight, because this is where things get really wild.
Okay.
XRISM has clocked gas moving towards us at a mind-blowing 930,000 miles per hour.
What?
And this isn't just a one-time thing.
Oh.
We're seeing these insane speeds consistently over multiple orbits of the system.
930,000 miles per hour. That's like traveling from New York to LA in less than a minute. But I thought black holes were supposed to pull things in.
Right.
Why is this gas being flung out at such incredible speeds?
That's the million-dollar question, and it's part of what makes Cygnus X-3 so fascinating.
Yeah.
We're not just seeing simple infall towards the black hole.
Right.
There's a complex interplay of forces at work.
Okay.
The stellar wind itself is incredibly powerful, and the black hole's gravity is creating this swirling vortex.
Right.
It's accelerating some of the gas to those extreme velocities. It's like a cosmic tug of war, and we're just beginning to understand the rules of the game.
Okay, so this spectrum is already painting a pretty intense picture, but you mentioned it's more complicated than a simple Doppler shift. What else are we seeing in this cosmic fingerprint?
Here's where the real puzzle begins. The spectrum isn't just telling us about gas moving towards or away from us. We're also seeing evidence that the gas is both emitting and absorbing X-rays simultaneously.
So it's like the gas is playing a cosmic game of hide and seek with the X-rays. That seems incredibly difficult to unravel. How do we make sense of all this?
That's where the power of XRISM's high-resolution data comes in. By carefully analyzing the subtle shifts and variations in the spectrum, particularly those related to ionized iron atoms, we can start to disentangle the emission and absorption components.
Hold on, ionized iron atoms? Why are those so important?
Think of them as beacons in the storm. Iron, when it loses some of its electrons and becomes ionized, emits and absorbs X-rays at very specific energies. And here's the key. Those energies are perfectly suited for XRISM to study.
So by looking for these iron fingerprints, we can get a much clearer picture of what's happening within this turbulent system. It sounds like we're going beyond just seeing the storm. We're starting to understand its inner workings.
Exactly. It's like having a cosmic microscope that allows us to zoom in on the most extreme regions of the system, where the gas is hottest and moving fastest.
This is incredible. We're talking about a system 32,000 light years away, and we can analyze the light to figure out how individual atoms are behaving. It's mind-blowing. But how does all of this help us solve the biggest mystery of all? Is there really a black hole lurking at the heart of Cygnus X-3?
That's the question that keeps astronomers up at night, and it's where the real detective work begins.
Okay.
You see, black holes are elusive beasts.
Right.
They don't emit light themselves, so we have to rely on their effects on their surroundings to infer their presence.
So we're looking for clues, like the way the gas is behaving, to build our case for a black hole.
Precisely. And one of the most important clues is the mass of the compact object. If we can determine its mass, and it's above a certain threshold, then we can be pretty confident we're dealing with a black hole.
Okay, but how do you weigh something that's 32,000 light years away and doesn't even emit light? It sounds impossible.
It's not easy, but it is possible. Remember that cosmic dance we talked about?
Uh-huh.
By carefully tracking the motions of the Wolf-Rayet star and the compact object over time, we can measure their orbital parameters, and from that, calculate their masses.
So it's like figuring out the weight of dancers by observing their choreography.
Yes.
I'm starting to see how astronomers can be detectives piecing together this cosmic puzzle. But I have to ask, with all this incredible data from XRISM, are we any closer to confirming whether that compact object is truly a black hole?
We're definitely getting warmer. XRISM's observations are giving us unprecedented insights into the dynamics of the system and the nature of the compact object. But as with any good scientific mystery, we have to be cautious and consider all the possibilities. There are other exotic objects out there, like neutron stars, which could potentially explain some of what we're seeing.
So even with all this amazing technology, it's still a bit of a cosmic guessing game.
Well, it's more like a process of elimination. We gather all the evidence we can, we weigh the different possibilities, and see which explanation fits the data best. And the more data we collect, the more confident we can be in our conclusions.
This is absolutely fascinating. We've gone from a mysterious system in the depths of space to analyzing X-ray spectra and weighing invisible objects. What other secrets is Cygnus X-3 holding, and how will XRISM help us unlock them?
It's like we've zoomed in from observing the swirling galaxy to examining the individual atoms caught in its dance. And with each new observation, Cygnus X-3 just reveals another layer of complexity.
Yeah, you mentioned earlier that Cygnus X-3 has been a favorite target for X-ray observatories for decades.
Right.
Why is that? What makes it such a popular cosmic laboratory?
Well, for starters, it's incredibly bright in X-rays, making it relatively easy to spot, even from a distance of 32,000 light years.
Okay.
But it's more than just how luminous it is.
Yeah.
Cygnus X-3 is a system in constant flux. It's a cosmic chameleon that's always changing, always presenting us with new puzzles to solve.
So every time we look at it, there's something new to discover. That's got to be exciting for astronomers.
Absolutely. It's like having a front row seat to a never-ending cosmic fireworks show. And the fact that we've been observing it for so long means we have this incredible historical record, like a treasure trove of data that allows us to track its evolution over time.
I imagine that kind of long-term perspective is crucial for understanding a system as dynamic as this. It's like having a time-lapse video of the system's life, showing us how it's changed over the years.
Precisely. And with each new generation of X-ray telescopes, our vision gets sharper, our understanding deeper. XRISM, with its unprecedented sensitivity and resolution, is allowing us to see details that were previously hidden, unlocking secrets that have been locked away for millennia.
Speaking of secrets, let's go back to those ionized iron atoms. You said they're key to understanding the complexities of the X-ray spectrum. Can you unpack that a bit more for us?
Imagine you're trying to understand a symphony.
Okay.
But all you have is this recording with all the instruments playing at once. It's a beautiful mess.
Yeah.
But it's hard to make sense of the individual parts. That's what we're dealing with in the Cygnus X-3 spectrum.
Right.
There's so much going on. Emission, absorption, gas moving at different speeds. It's all blended together.
Okay, so the ionized iron atoms are like our conductors, helping us to separate the different sections of the orchestra.
That's a great analogy. Ionized iron atoms emit and absorb X-rays at very specific energies, creating these distinct lines in the spectrum. And because iron is relatively abundant in the universe, those lines are often quite strong, even in a chaotic environment like Cygnus X-3.
So it's like having these little flags planted throughout the spectrum, marking the presence and motion of the iron.
Exactly. And by carefully studying how those lines are shifted and broadened, we can tease out information about the different components of the gas, how fast they're moving, and even the temperature and density of the material. It's like having a cosmic decoder ring that allows us to read the secrets hidden within the light.
Okay, so we're using these iron fingerprints to map the chaos, to make sense of this incredible cosmic ballet. But how does all of this relate to the ultimate goal of determining whether there really is a black hole in Cygnus X-3?
That's the question that drives all of our research, and it's where the evidence from the iron lines becomes especially important. You see, the way these lines are distorted and broadened can tell us a lot about the gravitational field in the immediate vicinity of the compact object.
So the stronger the gravity, the more distorted the iron lines will be.
Exactly. If the gravity is strong enough, the lines will become so smeared out that they'll be almost unrecognizable. And that's one of the telltale signs we look for when searching for black holes.
Okay, so if the iron lines in the Cygnus X-3 spectrum are super distorted, that would be pretty strong evidence in favor of a black hole, right?
It would be a major piece of the puzzle, but we need more than just distorted lines.
Okay.
We need to consider all the evidence. The mass of the compact object, its X-ray luminosity, the dynamics of the surrounding gas, and even the historical behavior of the system.
So it's like building a case in a cosmic court of law. We need multiple lines of evidence to convince the jury that a black hole is the culprit.
I like that analogy.
Right.
And like any good detective, we have to be careful not to jump to conclusions.
Yeah.
We have to consider all the suspects, all the possible explanations, and weigh the evidence carefully.
And I imagine there are other exotic objects out there, besides black holes, that could potentially mimic some of these effects.
You're right. Neutron stars, for example, are incredibly dense remnants of collapsed stars.
Right.
They also have extremely strong gravitational fields and can emit intense X-rays. So we have to rule out those possibilities before we can confidently say we found a black hole.
Okay, so it's a process of elimination, a cosmic game of Clue where we're gathering evidence and narrowing down the suspects. But even if we can't definitively say there's a black hole in Cygnus X-3, it sounds like we're learning an incredible amount about this system and the extreme physics at play.
Absolutely. Whether it's a black hole or a neutron star, the compact object in Cygnus X-3 is pushing the boundaries of our understanding of gravity, matter, and energy. It's a natural laboratory for studying the most extreme environments in the universe. And with XRISM, we're finally getting the tools we need to unlock its secrets.
What a journey this has been. We've gone from a mysterious X-ray source in the constellation Cygnus to decoding the secrets of superheated gas and weighing invisible objects. I'm already on the edge of my seat waiting for the next big discovery.
And who knows what surprises Cygnus X-3 has in store for us. This system has a history of defying expectations. And with XRISM keeping a watchful eye, I'm sure we'll have plenty more to talk about in the years to come.
And on that note of cosmic anticipation, we'll be back after a quick moment to delve into some final thoughts about Cygnus X-3 and the broader implications of these incredible discoveries. Don't go anywhere. We're back, and man, I'm still trying to wrap my head around just the sheer scale and intensity of Cygnus X-3. It's like this crazy cosmic demolition derby out there.
Yeah.
Gas is swirling at near light speed, X-rays blasting everywhere, and there's this compact object at the center of it all just kind of orchestrating the chaos.
Yeah.
You know, you've walked us through some mind-boggling science, but I want to bring it back to you, the listener. Why should we care about this system? It's tucked away, like 32,000 light years away.
You know, that's a great question. And it's one that scientists ask themselves all the time.
Right.
At first glance, Cygnus X-3 might seem like an anomaly.
Right.
A cosmic oddity that has little relevance to our everyday lives. But that's not the case at all. This system is like a living laboratory. A place where we can test our understanding of physics under the most extreme conditions imaginable. The densities, temperatures, and gravitational fields at play are simply beyond anything we can replicate here on Earth.
So by studying Cygnus X-3, we're essentially pushing the boundaries of our knowledge about how the universe works.
Exactly. It's like a stress test for our current theories.
Right. And sometimes those stress tests, they reveal cracks in our understanding.
Well,
For example, you said the spectrum of Cygnus X-3 is far more complex than we initially expected.
right.
We're seeing evidence of gas. It's both emitting and absorbing X-rays simultaneously.
Right.
And it's creating this intricate dance of light and shadow that challenges our existing models. You mentioned earlier the imbalance in the spectrum. There was stronger absorption than emission.
Right.
What's the leading theory to explain that?
Well, one possibility is that the dynamics of the stellar wind are playing a key role. So imagine the wind from the Wolf-Rayet star. It's like this dense fog of gas, constantly being blasted outwards.
Right.
Now, picture the compact object,
Okay.
likely a black hole, carving a path through that fog. As it does so, it creates a turbulent wake, a region where the gas is compressed and heated.
So the compact object is like a cosmic snowplow pushing the gas ahead of it and creating this dense, hot region.
That's a great way to visualize it. And this compressed gas in the wake could be absorbing a broader range of X-ray energies than the less dense surrounding gas, and that leads to the imbalance we observe in the spectrum.
Okay. That's fascinating. It's like we're not just observing a system, we're piecing together a story, a narrative of cosmic proportions. But let's be honest, there's still a lot we don't know about Cygnus X-3, right?
Absolutely.
Yeah.
The mysteries of Cygnus X-3 are far from solved. We're still debating the exact nature of the compact object, the details of its interaction with the Wolf-Rayet star,
Right.
and the mechanisms behind the extreme X-ray emissions. Each new observation raises more questions than it answers, which is part of what makes this research so exciting.
And that's the beauty of science, isn't it?
It is.
It's this never-ending quest for knowledge, a journey of discovery that continually expands our understanding of the universe and our place within it. But before we wrap up this deep dive, I want to leave you, the listener, with a final thought-provoking question. If Cygnus X-3 is indeed harboring a black hole, what are the implications for our understanding of the evolution of massive stars and the prevalence of black holes throughout the universe? Could systems like this be more common than we think, hidden amongst the billions of stars in our galaxy? Something to ponder as we continue to explore the cosmos and unravel its secrets. Thanks for joining us on this incredible journey into the heart of Cygnus X-3. Until next time, keep looking up.